Now, what I'm going to look at here, and again, not good to use this as the first thing you see. This is by far best if you are looking at this after having looked through the material, after having worked through some problems. If you're doing this instead of other, the things that I'm expecting you to do in addition to this, it's not going to work well for you. Well for you, it's just not designed that way. I'm not going to repeat that every time. That'll be the last time I do that for each one of these videos. Okay, let's start with looking at, let's see, sinusoidal waves, looking at this as the equation for the wave. The displacement in whatever x and y, or either the displacement is perhaps perpendicular to the direction of the wave, or maybe it's in the same axis. We'll look at each one of those two options as a function of the position of the wave in the direction of the line of the wave is moving, and time is the amplitude times the sine of some function k, well, some wave number k, in which k is 2 pi over lambda, minus, in this case, the negative sign means that the wave is heading toward positive infinity, omega, and omega is the angular frequency, 2 pi times the frequency, which is also two pi over the period, and phi naught represents some phase constant to account for the fact that perhaps we're not able to choose this such that, for whatever reason, the sign at x is 0, t is 0, maybe that's not 0. Maybe we have to account for that by accounting for some sort of phase shift. Now, what I want to look at here is how to connect this to how the wave is moving. Well, velocity is defined as the distance covered, well, the displacement covered, I should say, over the time covered. If I look at this as just v for speed, that's the distance traveled over the time. Now, if I were to envision looking at some wave moving, as I said, here toward positive infinity, let me take that particular branch of the wave and expect that I let that move the distance of that particular wavelength has moved over by one full position. Where I'm looking at this as frozen, I'm looking at this as very specific, locking down this idea of like, here's a particular position, x final, here's a position, x initial. It's moved between those two. So the distance, in this case, would be the one wavelength moved, and the time it took would be, by definition, one period. Now, there's two ways to get a velocity out of this. If we're looking at the wave itself, suppose I were to take this, and I were to take the speed of the wave is equal to the distance traveled lambda over the period t. Well, I can squeeze that out. If I'm given this equation, I can squeeze that out of that equation. But there's a way to do it that falls directly from this case. If we look at this, okay, let's see the velocity of the wave. If I suppose I multiply this by 1, which I'm allowed to do, and then shift that just a little bit, so I have lambda over 2 pi times 2 pi over the period. Notice what that gives me is that the velocity of the wave is equal to, well, 2 pi over period is the angular frequency, omega, and lambda over 2 pi is 1 over the wave number, so I've got 1 over k. So the movement of the wave itself, which I can also write as lambda times the frequency, because the frequency is 1 over the period, I can write that as the wavelength times the frequency, or the angular frequency divided by the wave number. So that's the speed of the wave itself. Suppose I'm looking at, heck, I won't even say speed. I'll go ahead and say velocity here because it's going to keep directional information. The velocity of a point on the wave. For example, a point in this material here, as the wave moves, that piece of, this happens to be, say, a string, and I've got a wave traveling through a string. Then what I'm going to have happen is that piece of the string will be moving up and down. And it will not be moving up and down with the speed of the wave itself. That motion is toward positive infinity. To find that out, I need to use calculus and say, okay, the velocity of that point is the derivative with respect to time of the displacement, which is, okay, now the derivative of a constant, that stays there, so because the sine is a function of time. So, in order to find the time derivative of sine some stuff, I first take the derivative of sine, which is negative the cosine of whatever is inside, kx minus omega t plus phi naught. And then I have to take the derivative of the interior. I have to take the derivative of the function. So, the derivative of kx with regard to time is 0. The derivative of a constant is 0. So I have the derivative of negative omega t, which is simply negative omega. So the velocity of a point on the string, as it were, will be omega times a, the amplitude, times the cosine of kx minus omega t plus phi. If I take that derivative one more time to find the acceleration of a point on the string, that's taking this derivative one more time. That's the derivative of the cosine, which is the sine. Then the derivative of the interior, which again just gives me another negative omega, so negative omega squared a times the sine of kx minus omega t plus phi naught, or the acceleration of a point on the string is equal to negative omega squared times the original the function describing the displacement. You know, a sine kx minus omega t plus phi naught.